So logarithms, this is a bane for some students, and they're really not too bad. I mean, if you just remember these two ways to think about logarithms. When I have a base and it's raised to a power, that's an exponential expression, especially if it's you get a variable in a number and a variable. But it also works with just numbers. The base raised to the power equals the answer. Now, if you want to write that as a logarithm, all a log is asking us, it says, what power do I have to raise that base to in order to get that answer? And of course, that's what the expression is. So if you think about, look at this first example, it says 2 to the third equals 8. So if I wanted to write that as a log expression, I would write log, then it's base 2, and the answer over here is the 8, and that's equal to 3. And if you notice, here's my base, 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 answer, 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 exponent, exponent, exponent. And that's all it is. Now we can go back and forth between a log format and an exponential format, and depending on what you're trying to do with it, one way is easier to deal with it than the other. For this next one, 5 to the p equals q. Well, stop the video, try to write this as a log expression, then come back and watch what I'm doing with it. So, the log, the base is 5, the answer is q, and the exponent is p. Now, the other thing that some people have a hard time with, and I didn't want to do this earlier, you have an imaginary line that you're writing here. This is like having the line on a piece of paper, a writing paper. The base needs to be like a subscript. Okay, so everything else is on the same line, but the base is subscripted. Just like the exponential form is a superscript. Okay, so hopefully don't forget, everything we're going to do with logarithms all comes back to this. So now, thinking about what we just did. For the first part, base is 3. So it's going to be 3. The exponent, see that 3 there is the base. The exponent's over here. So that's 3. And that equals the answer, which is 27. And yeah, 3 times 3 times 3 is 27. So again, stop the video, try letter B here, see if you can do it. So it's going to be 4 raised to the k equals n. And so the base is 4, the number over here is the exponent, and that's the answer. There's a more mathematical term for that. I don't remember what it is. It's one of those archaic things that we don't need to worry about. Okay? For the good stuff, how do you solve that? How do you solve that equation? Well, let's get the log is the problem. So let's get rid of it by writing this as an exponential. So I'm going to say 2 is the base, 4 is the exponent, x is the answer, and of course 2 to the 4th is 16. So x equals 16. So now we've got to get rid of the exponent, because it's 2 to some power is 12. So if we rewrite this as a logarithm, all right, log base 2 of the answer, which is 12, equals x, and that is an exact value. It's not a approximation. It's not a decimal value. It's not a really useful answer, really, but that is the answer. Now, while we're thinking about this, you can use your calculator, and some of the newer calculators actually have a feature where you can change different bases, use different bases. But there's this formula, and that's one of the objectives for this lesson. It's called the change of base formula. And all that says, if I'm trying to evaluate some logarithm that's to some base, see on your calculators you've got a log button. You also have an ln button, and that log button is log base 10, and you'll see that in the next slide. And the ln button is log base e, and we'll see that on the next slide too. So you do have a log button in your calculator. And so what you can do is, in order to evaluate this and get a decimal number, the change of base formula says, hey, you take the log of the answer, so to speak, divided by the log of the base, and that will equal what this is. You can also use ln. You can use the natural log. So ln b over ln a. I don't like my ln, but I'll write it like that. So you'll get the same answer, and you could test this out with your calculator. You could take the log of 12, and you probably have a parenthesis, and you're going to have to hit the divide key, and then write log 2, and you'll get some decimal number, some answer. And if I write ln, I meant to write ln here. If you were to do ln natural log of 12 divided by the natural log of 2, you'd also get the same answer. And so this is called the change of base formula, because I'm changing this expression from base 2 to base 10 if I'm doing this one, or base e if I'm using this one. Let's see, do I want to talk about anything else here? Oh, I think we're good. One more thing I wanted to talk about. I know this is not going to be a nice, neat whole number, because I know that 2 to the third power is 8, and I know 2 to the fourth power is 16. So in order to raise 2 to some power and get it to be 12, well, that tells me the answer is going to be somewhere between 3 and 4. Because 2 to the third is 8 and 2 to the fourth is 16. Okay, so that's one way to estimate if your answer is reasonable. Now they're asking us to evaluate this stuff, these expressions, without a calculator. And here, I knew I'd put this in here. Whereas the common log is base 10, and the natural log is base e. And we write it ln, natural log. Some people ln, some people call it. I've always called it ln because I had some professors said that one time. So. All right, so here's what this is asking us. Evaluate that. Well, what it is, we know, remember how we just said that if there's no number there, it's base 10? And I don't know what this answer is, so they're telling me, hey, 10 to some power equals 1,000. Well, I know that 10 times 10 times 10 is 1,000, so I know that that expression is actually equal to 3. Being able to do this by hand without a calculator is an important skill. Okay, this one, log of 1 over 100. Well, I can do a couple of things here. I can say I know that 1 over 100 is the same thing as 100 to the negative 1. I also know that 100 is 10 squared. So log of 10 to the negative 2 is the same thing as log of 1 over 100. Now there's this property here that we're going to think about. Well, let's see. Let's just rewrite this as an exponential maybe. How do I want to tackle this? So I know that 10 raised to some power equals 10 to the negative 2. Well, since that's just rewriting as a log, which just like what we've been doing so far. Since that base is the same, those exponents have to be the same. So it's equal to negative 2. There's one log property they introduced in this section. It's the exponent rule. And I think that'll help us with part C, though, I mean, we could do this part C with this exact same thing, and I probably will. The log property that I want you to see is if I have log base A of b to some power, it doesn't have to be a variable. I wrote x. The property says, hey, you can bring that exponent down in front of the logarithm, and it'll be the exact same thing. Okay, there's some domain issues when you start dealing with functions, but for the most part, it'll let us evaluate. These expressions are all just things we're evaluating. So to think about applying that property to this expression, log of 10 to the negative 2, what's that equal to? Well, I can bring the negative 2 down in front. Then this says log of 10. Well, 10 to what power is 10? Well, that's going to be 1. So the answer is negative 2. And of course, that's the exact same thing we got this way. So thinking about this ln expression, remember ln's natural log. I can think of this as ln e to the 1/2, because taking the square root is the same as raising it to the 1/2 power. So I could use that log property, bring the 1/2 down in front if I want. And this says e to some power is e, well, that's 1. So that expression is going to be 1/2, because 1/2 times 1 is 1. Some people I've had, and it works, it certainly works to do that, the ln and the e cancel out. They do. The log and the 10 cancel out because they're the same bases. So if you want to think about it that way, that works, as long as your base is the same. If I have to evaluate log base 2 of 2 to the 5th, well, that says 2 to some power equals 2 to the 5th. X has to be 5. The log and the exponentials cancel out because it's 2. Hopefully that helps. So now they want us to evaluate this using your calculator. I don't have a calculator to snap a picture of, but you probably have a log button on it, and you would type log 700 equals, and they'll get some decimal answer. And that's all you really need to worry about there. If they ask you to find the natural log, you have your ln button. Now we've got this equation that we have to solve. Well, it's got a couple of things going on. It's got this stretch. Oh, maybe we should talk about graphically. So what this is looking at is I've got some exponential growth equation going on here. I mean, I know it crosses the y-axis at 5, 0, 5, and that's from our earlier work, because when x is 0, that's 1.3 to the 0 is 1, so times 5. But what they're asking us, when does this graph equal y equals 10? And that's what we're doing. It's certainly, you know, if I'm not specifying and you want to do something graphically, do it. People that are taking AP Calculus next year will need to be able to do this. They'll give you some god-awful equation, and you want to know when they're equal, or two equations when they're equal to a value or something, or when they intersect, and you want to be able to do that with a calculator. We can also do this algebraically. It's not too bad. At least we won't be able to do it all without a calculator, but we can certainly set it up. I'm going to solve this for the base. So I'm going to divide both sides by 5. That gives me 1.3 raised to some power equals 2. And then we can think about this as rewrite it as a log expression. It wouldn't be wrong to do that. I'm thinking it might be easier to use that log property though. If we take the logarithm of both sides of this equation, that's 1.3 to the x equals log of 2. I can use that log property about that exponent coming down in front. What that does for me is I can write this as x log of 1.3 equals the log of 2, and then just divide both sides by the log of 1.3, and that'll leave the x by itself. I can grab my calculator and do log 2 divided by, to make sure you can do this in your calculator, you'll do log 2 divided by log of 1.3. Proper use of parentheses is important. You could skip this one, but this one you've got to close. If you don't close this parenthesis, that's going to take 2 divided by the log of 1.3, then take the logarithm of that answer. Okay. So another problem, this is base e. So same deal, we're gonna divide both sides by 6. That leaves me e to the 3x plus 1 equals 3 over 2. I'm reducing that fraction. And then we're going to take the ln of both sides. Now, here's what's so cool about this. If I take the ln of this, remember how ln and e will cancel out? Or you can think about the exponent coming down in front, doesn't matter. But the bottom line is, on this left-hand side, I just have the 3x plus 1. And on the right-hand side, I have the natural log of 1.5 or 3 over 2. And then, so you're going to grab your calculator. Well, actually, I'm going to subtract 1. Then divide that answer by 3. So on my calculator, I would type in ln of 1.5, close it, subtract 1. I'd probably hit equals, and then I would divide by 3. And that'll be what that answer is. So the same kind of deal with this one, except we're going to subtract 6. So I'm gonna get 2 times 1/2 to the t equals 4. Then I'm going to divide by 2. So 1/2 to the t equals 2. And then what we can do is we really don't need a calculator for this. We could think of this as 2 to the negative 1 times t, or raised to the t power, equals 2. So 2 to the negative t has to equal 2 to the first. So it must be, since those bases are equal, negative t equals 1. So t has to equal negative 1. And you could do all that with a calculator if you wanted to. I just wouldn't be wrong to. Now we've got a couple of word problems. You got to go back to thinking about what we did earlier and back in section 1. If I'm going to write an exponential equation, I have my initial value, I have my growth rate. This is growing 7% a year. And you go plus 1. There's no compounding effect going on here, so we don't have to worry about that. So tuition started at $10.50. It's growing at 7%, so I'm going to make that as 1 plus 0.07 to the t power. That leaves me an equation, 1050 times 1.07 to the t. And they want to know, when is the tuition going to exceed 2,000? This must be per credit. It must be some expensive college. So I'm going to divide by 1050. So that leaves me 1.07 to the t equals whatever that answer is. I'm not going to be lazy with this one. I'll actually do some calculation. Okay, my calculator says that is 1.905. I rounded to 3 decimal places. Honestly, I'm just going to leave the full value on my calculator and not round. So I might get a slightly different answer. So now what we're going to do to get that exponents a problem, we're going to take the log of both sides. What that lets me do is it lets me say t times the log of 1.07 using that exponent property equals the log of 1.905. I'm going to divide both sides by the log of 1.07, log of 1.07, and that's going to tell me that t is, it's a little dark, but it's looking like the answer to that equation is 9.5. So not quite 10 years. During the 9th year, the tuition will have grown that much. Okay, so here's the last, and this is kind of I really like using these problems. The population grows 10% each year. They want us to change that to a continuous growth rate. So if you go look in the book, here's our annual growth rate, where I have 1 plus r is our annual growth rate, and I want to know, when is it e to some k. See, this is raised to some time, and this is raised to some time. So that would be the situation. What we want to do is be able to take this continuous growth rate, this annual growth rate, and change it so it's e to a power. We could go backwards too. And in fact, why don't I? Just to go back, to show you. So I'm going to write 1 plus 0.1, because 10% becomes 0.1, has to equal e to the k. Because we know they both have a t with it, right? So when is 1.1 equals e to the k? Well, I want to get rid of that e, so the way I get rid of the e is I'm going to take the natural log of both sides. So the natural log of 1.1 will be equal to k. And my calculator is telling me, well, let's see. My calculator is telling me 0.09531. So I'm going to say that that's an annual growth rate, a continuous growth rate of 9.5353%. And that happens because when it's a continuous growth rate, your interest is continuously being compounded, increased. Okay, so it's a little bit lower than the 10%. Now, if I wanted to go back to a annual growth rate, and they gave me the continuous growth rate, I would just have to say e raised to that 0.09531, and I would get pretty darn close to the 10%. Okay, I rounded, of course. If I didn't round on my calculator, I'd get that back. So I hope that helps you answer the questions in My Open Math and out of the textbook. Encourage you to do both. Let me know.